In this example circuit, we know the battery's voltage and we know the resistances of all the resistors and how they're arranged. But we are missing what information? What else could we calculate from this information? Yeah, we don't have any information about current, but with the voltage of the battery and the resistances of the resistors, we should have enough information to calculate all the currents. So I think it would be a good idea to start by labeling all of the, and without even knowing the value of the current, we can at least label all of the currents we're going to get with variables. And in this setup, how many different currents would you expect to have? And why 5? We do have 5 different resistors, but some of them can be guaranteed to get the same current. Can you identify any pairs of resistors that have to get the same current as each other? Or under what circumstances would you expect 2 resistors to have the same current? Generally, if resistors in parallel, they could have different currents, but they have to have the same voltage drop. So let's take a look at that first, the idea of series versus parallel. If you have some resistors in series, let me draw that out first. Let's say we've got resistors in series, like you've just got a section of wire, regardless of the shape. In fact, the shape doesn't matter at all. If you have something like this resistor and this resistor, but they're connected like this, then those 2 resistors would be in series with each other because they're on the same path. You've got current coming in through one of them and current going through the other one. Just like any 2 points in the same single pipe will have the same fluid current, any 2 points along the same path of wire are going to have the same electrical current. So if you trace out the current flowing through here, current flowing into this resistor, and then around this corner and through this resistor, it's all the same current. There's nowhere else for it to go. So that's the main defining attribute of any 2 resistors or 2 or more resistors in series. If any resistors are in series, then they have to have the same current as each other. And can you identify any resistors that are in series here? Yeah, R3 and R4 are in series with each other because they're along the same path. If you take a look at resistor 3, let's say you've got current flowing through resistor 3, the only place for that current to go is continuing through resistor 4. And then also continuing around this branch, this corner here. This is all one path, so those all have to have the same current. Let's call that, let's say I3, because it's the current through resistor 3 and also resistor 4, which has to be the same current. So current 3 is some unknown value, but it's at least the same current through resistors 3 and 4. As for 1, 2, and 5, let's say we've got current going through resistor 1. Let's call that current I1, which we don't know yet. But what happens to that current when it hits this junction here? Yeah, the current's going to split. So that means the current through resistor 1 is not going to be the same as the current through resistor 2. Resistor 2 gets a different current. Let's call that current I2. Which we also don't know. What about resistor 5, though? Does that have the same current as anything else in the system? Yeah, resistor 5 and resistor 1 are along the same path. This path here, that path is all just one single path. Whatever current is flowing through resistor 5 continues through the battery and continues through R1. That's all the same current. It's the same flow rate. When it hits the junction, it's going to split into two new currents, I2 and I3. But as long as you're just going through wire or resistors or batteries or anything with no junctions, just a single path, the current has to be the same everywhere along the path because there's nowhere else for it to go. So resistor 5 is also that same current I1, as is the battery, but we generally don't really care what the current through the battery is. The important thing is current as it passes through resistors. And generally any resistors in series, such as R1 and R5 on the same path, or R3 and R4 on the same path as each other, any resistors in series like that have to have the same current by definition. You can also think of this as a junction rule thing. If you draw out any region, like if we just trace out some region of the circuit, let's say we just draw a blob here. The junction rule says that the total current going into that blob has to match the total current going out of that blob. We have current going in and current going out of that region. The current going in and the current going out of that region have to match each other. In other words, the current going through resistor 5 has to match the current going through resistor 1. Same thing if we draw the similar blob at, let's say, the upper right corner. If I draw this blob here, the current flowing into that corner, that is through R3, has to match the current flowing out of that corner through R4. So that tells us from the junction rule that resistor 3 and resistor 4 are getting the same current, which we would just call I3. But if we draw a blob around the actual junction, what does the junction rule tell us about these three currents? What do we know, or what can we write? Not the resistances, but the currents. So we write that in terms of the currents. The total current going in is I1. The total current going out of this region would be I2 and I3 combined. So I2 plus I3. That's the junction rule. If you draw any region that wires are going into and or out of, the total amount of current flowing into that region has to equal the total amount of current flowing out of that region. So in this case, we say I1 equals I2 plus I3. And that at least tells us how these unknowns are related. We've got three unknown currents, current 1, current 2, current 3. So ideally, we want to have at least three equations describing how they're related. One of those equations can be the junction rule. That's an equation describing how these are related. Any questions on that so far? And if we try using the other junction, we just end up with the same equation. Current in is I2 plus I3, current out is I1, so we still get I1 equals I2 plus I3. And it's a good idea to check every junction in the circuit with the junction rule, but often they'll lead to the same equation anyway. In a more complicated circuit, you might get several equations from the junction rule. In this case, we just get two copies of the same equation. So we still need more information here. Any questions on the setup so far? So let's take a look at another sort of arrangement. If we have, let's say, the same two resistors we were looking at earlier, but we arrange wires like this. So we've got an incoming wire that splits into two paths, each path having a resistor, and then the wires joined back together to one path. How would you describe how those resistors are connected? Series would be if they're on the same path, like in this one on the left here, that the current going through one of them has to be the same as the current going through the other. Yeah, these ones I would describe as in parallel because it branches off into separate paths and then joins back together. Most importantly, these two paths start at the same point and end at the same point. If we call this like location A and location B, each one of these paths is the path that starts at location A and ends at location B. Starts at location A, ends at location B. So both of these resistors, or both of these paths, I should say, start from the same location and end at the same location, which means what has to be the same about both of those paths? If they have the same starting point as each other and same ending point as each other, what has to be the same about both the paths? Yeah, they've both got to have the same voltage drop because location A has some amount of voltage, location B has some amount of voltage. For the top resistor, delta voltage would be voltage B minus voltage A. For the bottom resistor, delta voltage would also be voltage B minus voltage A. They both have the same full voltage drop. The same full delta V, same full voltage drop, because they're both starting at the same high voltage and they're both ending at the same low voltage. So they both get the full delta voltage from A to B. Like for instance, let's say we know these voltages. Let's say we know that voltage A is 10 volts. And we know that voltage B is 7 volts. If you go through the top resistor, you're losing 3 volts. If you go through the bottom resistor, you're also losing the same 3 volts. So each one of these resistors would have delta V equals negative 3 volts. Any questions on that so far? Whereas what happens to the current? If you've got some amount of current flowing in, what's going to happen to the current when it hits the junction here? Yeah, the current's going to split. So in parallel, each resistor gets the same full voltage, but they have to split up the available current. Maybe you've got like 50 amps of current coming in and it splits into 40 amps and 10 amps. So we'd still have the junction rule. Incoming current equals the two outgoing currents, the currents through the two branches added together. So they split up the available current, but they both get the same full delta V. Any questions on that so far? Whereas if they're in series, they have to get the same full current. But if you take a look at the delta V, let's say you start with some high voltage, you lose some of that voltage going through the first resistor, so now you're at some medium voltage, and then you lose more voltage going through the next resistor, so you're now at some lower voltage. So in series, they both get the same full current, but they have to split up the available voltage. Any questions on that so far? And can you identify any paths in this diagram that are in parallel with each other? Any paths that start at the same point and end at the same point? For parallel, yeah, we might not know in advance how the current splits. So for instance, let's say the incoming current is, let's say 10 amps. That might split into 5 and 5, or it might split into 7 and 3, or 9 and 1, or 9.5 and 0.5. The important thing is the two paths have currents that add up to the original 10 amps. But at the next junction, those will merge back together. And so the outgoing current here will be 10 amps again. But while it's in the parallel network, it's going to split into, we don't know yet, maybe 7 amps and 3 amps, for instance, or 6 and 4, really depending on how these resistors balance against each other. When would you expect the split to be equal, though? Like if you got 10 amps coming in, is there any circumstance where you would expect it to split exactly 5 and 5, half and half? That is there any reason why there wouldn't be a preference for more of it to go one way instead of the other? When would you expect it to go exactly half and half split? It doesn't really matter about the battery. The battery just provides a push. In fact, the battery doesn't really provide charge at all. The charge is already there. The wire contains as much charge as we're ever going to need, both positive and negative. The battery just provides a push that we call voltage. But how the current splits, I mean, the voltage of the battery influences how much current flows in the first place. But how the current splits depends only on the paths themselves, specifically the resistances. Generally, we would expect the path with less resistance to get more of the current, and the path with more resistance to get a smaller piece of the current. But if these two paths have the same resistance, then they should be expected to have equal amounts of current. The current would split evenly if the two paths have the same amount of resistance. And I think for figuring out what counts as parallel or not, it can kind of be difficult to see from the diagram originally. But a very useful way of looking at that is mapping out what we usually call nodes. A node just represents a region or a collection of points on the wire that are all the same voltage, all connected by just wire. For example, if we take a look at, let's say, the point right before the battery. What else is connected to that by just wire? Is there anywhere we could go from there without going through anything except just wire? The thing is, if you go to the other side of the battery, those 2 points are different regions. They're separated by the battery itself. You can't get from here to here by just going through wire. So we would consider those to be different regions. What I mean is, if you start at some location and just travel as far as you can by going only through wire, we get this region here. This sort of corner is as far as you can go traveling along only wire and not crossing over any batteries or resistors or capacitors. So what does that tell you about the voltage everywhere along this region? Uh, 98 volts is not the voltage of this region. 98 volts is the difference in voltage caused by the battery. The important thing about any points connected by wire is that they're all at the same voltage. The idea being that delta V of wire is always going to be 0. That is, if you have any two locations connected by wire, they're all at the same voltage. There's no difference in voltage. So we would say all the points along this region are all at the same voltage as each other, because there's nothing between them that would cause a difference in voltage. And conventionally, we usually call the location at the negative terminal of the battery 0 volts. We don't necessarily have to, it's just convention. But the important thing is if you cross over the battery, you get to a different voltage. So for example, this region here, at the positive terminal of the battery and everywhere connected to that by just wire, that's another node. That's another region that's all at a certain voltage. So this region is all the same, all a single value of voltage, which is different from the voltage down here. And specifically, the battery provides a 98-volt difference between those two regions. The region at the positive terminal is going to be 98 volts higher than the region at the negative terminal. And conventionally, we usually call the negative terminal 0 volts. We don't necessarily have to. We could call this any voltage we want. But it usually makes it easier to understand if we call that region 0 volts. And then the battery creates a 98-volt difference. So the positive terminal is 98 volts higher than 0. In other words, 98 volts. And again, it doesn't have to be 0 and 98. You could call the low voltage 1,000 volts, and then the higher voltage would be 1,098 volts. It doesn't matter what numbers we use. The important thing is the difference between them. So the battery creates a difference of 98 volts, a difference between a low voltage zone at its negative terminal and a high voltage zone at its positive terminal. But any two points connected by just wire must be at the same voltage. Any other questions on that so far? And let me label these zones also. Or actually, let's expand this a little more first. If you cross over the next resistor, you get to another zone that's all different voltages. So the zone after resistor 1 is another node, another region that's all a single voltage. And you can imagine that point spreading out to all locations that are the same voltage, that is all connected by wire. So if you spread out from here to all the locations connected to it by just wire, this sort of T shape at the top, all those locations are connected by just wire, so they're all at the same voltage as each other. It'll be different from 0 and 98, presumably somewhere in between, but it'll all be at a single value of voltage. Likewise, if we cross over R3, we get to another region. This region would all be another node. It would be another single value of voltage. So all these points in the upper right corner are a single voltage value shared with each other. And then if we cross over R4, we get to one more node. This entire region down here, all these points connected by just wire, all these locations are another node. They're another region that's connected by just wire. So that's another region that's all the same voltage as each other. Any questions on that so far? So how many nodes do we have here? Yeah, and with 5 nodes, that means there's only 5 values of voltage in this entire circuit. And of course, what we care about is the differences between those 5 values. But those 5 values are going to be the only 5 values of voltage in the whole circuit. And often the idea of nodes makes it possible to redraw the circuit in sometimes a much easier way. Like we have, if we just draw these 5 nodes as single points, let's try that out. If we just draw each node as a single point, like we've got, and let me label these. Let's say we call these node A, node B, node C, D, and E. Let me look that in a different color. Yeah. Okay, so let's say we have labeled these 5 nodes. If we treat each of those nodes as a single point, it often makes it easier to see what's going on. So if we just draw node A, node B, node C, node D, and node E. And we'll go ahead and label those. With these nodes labeled, it's often easier to redraw the circuit in an equivalent way. And that sometimes makes it much easier to see what's in series and what's in parallel. For example, if you consider node A, what's actually attached to node A here? What things are actually connected to node A? Yeah, we've got one resistor and one battery. Specifically a battery connecting node A to node B. So we could draw that in. And then we've also got the resistor 5, connecting node A and node E. So we could draw that in. And we should label those. And what else do we have here? For instance, what else connects to node B? Yeah, we've got resistor 1 connecting node B to node C. So we could draw that in. Resistor 1. And then if we just fill in the rest of the resistors, for instance, resistor 2 connects from where to where? If you have two batteries that are in series with each other, you can just add up their voltages and treat them as one battery. But also it's very helpful to treat that as node analysis also. You can just mark the nodes like we've done here, and label a voltage at each node, and keep in mind that each battery creates a difference in voltage, a constant difference in voltage, with the negative terminal being at lower voltage and the positive terminal being at higher voltage. What else connects nodes to nodes here? Do we have any other resistors we need to take into account? Yeah, C has resistors 2 and 3 branching off of it, 2 different destination nodes. Resistor 2 goes from C to E, and resistor 3 goes from C to D. And the shape of the wire doesn't matter here. All that matters is what connects to what else. So resistor 3 is a 7 ohm bridge from node C to node D. And resistor 2 is an 8 ohm bridge from node C to node E. And lastly, we've also got resistor 4, connecting D to E. So R4 is 5 ohms. And in this diagram, can you see any paths that start at the same node and end at the same node? B and A, the thing is that includes the battery. The battery is usually not all that useful to look at there, because the battery we know creates a voltage difference. If we actually label those, we've got voltage A is we're calling 0 volts. And voltage B we're calling 98 volts because it's 98 volts higher than voltage A. But let's say you're at location C. How can you get from location C to location E? You can go through R2, or alternatively, how else could you get from C to E? Yeah, you can go through R3 and R4. So that means those two paths, the path through resistor 2 and the path through resistors 3 and 4 together, those two paths are in parallel with each other. In other words, they have to have the same delta voltage. The delta voltage across resistor 2 has to match the delta voltage across resistors 3 and 4 together. And this can be very useful for combining the resistors also. For example, first of all, resistors 3 and 4, we'd have to deal with those first, because we can't say resistor 2 is in parallel with one or the other of them. Resistor 2 is in parallel with 3 and 4 together. So we'd want to combine 3 and 4 first. And 3 and 4 together act like how much resistance in total? Yeah, since they're in series, we can just add them together and say resistors 3 and 4 together act like just 12 ohms. So let's set this aside for the moment and replace it with just a single 12 ohm resistor. And we could call that R34 as the combination of 3 and 4. And that 3,4, the 12 ohm resistor is definitely in parallel with the 8 ohm resistor because they both start at C and they both end at E. So if these are in parallel, how would you combine their resistances? How would you combine 8 ohms and 12 ohms if they're in parallel with each other? Yeah, we can add their inverses. Instead of adding 8 plus 12, we would add the inverses of 8 and 12 and then invert the result. So 1 over R equals 1 over 8 plus 1 over 12. And the common denominator for those would be 24 would probably be easiest. So we've got 3 24ths plus 2 24ths. In other words, 5 24ths. Invert that again, we get resistance is 24 fifths, which is 4.8. 4 and 4 fifths. So that means the two of these together act like a single 4.8 ohm resistor, weaker than either one individually because paths in parallel make it easier for current to flow. So let me move this aside and we'll treat this as R234 altogether acting as 4.8 ohms. And at this point, we essentially have just one single path. So how would you say these three resistors are combined with each other? Yeah, these are now in series, so we can just add them together. 3 plus 2 plus 4.8 would be 9.8 ohms. So we could say altogether, these act like a 9.8 ohm resistor. And if we've got 98 volts battery and 9.8 ohms of resistance, how would you calculate the current through this equivalent circuit? Yeah, well, voltage, current is voltage over resistance, yeah. Because if we write out the loop rule for this, generally the sum of the delta voltages in a loop should add up to 0. In this case, the delta voltages are just the battery, which is 98 volts, and the delta voltage of the effectively one resistor, all the resistances added together, or all the series resistances added together. So for the battery, we just got plus 98 volts. And what's delta V for any resistor? If it was 0, wire has resistance of 0, but this isn't just wire. These are resistors. Any resistor has a resistance that's a delta voltage that's proportional to current, specifically negative current times resistance. The more voltage the resistor has, the more delta voltage the resistor has, the faster current will flow through it. And then resistance is the constant of proportionality, and the negative sign refers to direction, that the current will flow from the high voltage end toward the low voltage end. So we can write the delta V of the resistor as negative I times R. But we already found that the equivalent resistance is 9.8 ohms. So 98 volts from the battery plus negative current times 9.8 ohms from the equivalent resistance equals 0. And then how would you solve that for current? Algebraically, if you isolate I in this equation, what do you get? Yeah, negative 98 divided by 9.8, and that'll be 10. So that means the current in this path is 10 amps, volts over ohms being amps. And in the original circuit, which one of these three currents is that 10 amps going to represent? What's the one part of this circuit we didn't simplify? We didn't combine with anything. We combine all the resistors together, but what's the one piece of this circuit we didn't have to simplify? Yeah, point A and B and the battery between them. So that means that battery between points A and B is the one thing we didn't simplify. So that means that's the one thing that has the current that's guaranteed to have the current we just calculated. That 10 amps is specifically the current through the battery, which also happens to be the current through resistors 1 and 3. So we can fill that in. Current 1 is 10 amps. And so generally you simplify the circuit, combining all the resistors into one big equivalent resistor to figure out the current through the battery or through the main branch. Once you've got that, go back to the original circuit and you can figure out all of the voltage differences on that branch. So let's try that. Let's go back to the original circuit Let me put these back. And now we can start calculating voltage differences because we now know the current. For example, we now know that the current through the battery and R1 and R5 is 10 amps. So if we fill that in, we now have the current and resistance in each of those. And if you know current and resistance, what can you calculate? What do you get if you multiply current times resistance? I times R equals what? If you go back to the formulas we've got up here, current times resistance tells you the delta voltage, tells you how much the voltage changes from one end of a resistor to another. So for resistor 1, for instance, we know the resistance is 3 ohms and the current is 10 amps. If you multiply those together, what do you get? Yeah, negative 30 volts. So that means as you go through this resistor, you lose 30 volts. At point B, we had 98 volts. Going through resistor 1, we lose 30 volts. So at point C, the node C, we end up with 98 minus 30 would be 68 volts. So the voltage at node C is 68 volts, since we started at 98 and we have lost 30. Any questions on that so far? And we don't really know how that 10 amps splits up. We know that the current through 3 and 4 plus the current through 2 has to add up to 10 amps, but we don't know exactly how it splits up. But what we can do is going back to resistor 5, we know for resistor 5, we have the resistance and we have the current. If you multiply that current times resistance, what do you get? Yeah, 20 volts. So that means on this resistor, delta V is negative 20 volts. We started at something at node E, we lose 20 volts, we end at 0. So what did the voltage at node E have to be to make that work? What do we have to start at so that we can lose 20 volts and end up at 0? Yeah, we had to start at positive 20 volts. Or more generally, we had to start 20 volts higher than whatever this was. But we're calling this 0, so we have to call this one 20 volts. And at this point, we now know enough information to continue. Because we know the voltage at C, we know the voltage at E. What's the change in voltage between those? What's the difference between those? Right, which means resistor 2 is getting negative 48 volts as its voltage difference. And at this point, for resistor 2, we know the voltage and the resistance. So we can once again go back to delta V equals negative IR. Here we know the delta voltage, negative 48 volts, and we know resistance, 8 ohms. So how would you calculate current? Yeah, take that delta V, negative 48 volts, divide by negative R, negative 8 ohms. 48 over 8 is going to be 6. So that means that gets 6 amps of current. So the current here through resistor 2 is going to be exactly 6 amps. And that's the I2 from the original diagram. And we could continue with voltages, dealing with R3 and R4 together, also using up 48 volts because they're in parallel. But what do we know about I1, I2, and I3 together? How are those related to each other? If we go back to the junction rule from the very beginning, we know I1 has to equal I2 plus I3. So if we fill in those values, we know, for instance, I1 is 10 amps. We know I2 is 6 amps. What does I3 have to be to make this work? Yeah, that's got to be 4 amps. So now that we can fill that in, that the current through resistor 3 and resistor 4 is 4 amps. We can now calculate one last, or I guess 2 last delta voltages. For instance, across R3, we know we got 7 ohms of resistance times 4 amps of current. Multiply those and what do you get? Four amps times 7 ohms gives us how much? Yeah, 28 amps. So that means through this resistor, we're losing 28 volts, or 28 volts, because amps times ohms is volts. So at node C, we started with 68 volts. We lose 28 volts. So at node D, 68 minus 28 would be 40 volts. And then through resistor 4, multiply current times resistance, 4 amps times 5 ohms is 20 volts. So we lose 20 volts and we're down to 20, which is exactly what we already had for node E. So that matches up. We now have all the currents in the entire circuit. We know the voltage at every node, the current through every path, and that's pretty much everything we need to know about the circuit. If you want to know how bright these bulbs are, assuming they're bulbs, light bulbs, you could then calculate power using any of the power formulas because we know everything else about the circuit now. Any other questions on that? And if you want to get some more practice on this, take a look at math.ncheese.org/P7B. There should be a practice worksheet of a whole bunch of circuit diagrams. And similarly, those give you the voltage of the battery and the resistances of the resistors. And the challenge is find the current everywhere. Try this node analysis approach on those. Identify all the nodes, the locations that are just regions of wire between resistors or batteries or whatever. Those regions are all a single voltage. So you can mark them as just effectively a single point. Redraw the circuit as this sort of a graph diagram with single points connected by resistors or batteries or wires or whatever. And then see if you can figure out the current through every path and the voltage at every node. If you can find that information, that's pretty much everything you need to know about the circuit. So to give that a try, let me know if you have any other questions, and I will see you next time. You're welcome.